A central idea in any anatomy and physiology class is the concept of homeostasis, or maintaining a relatively stable internal environment. I think intuitively we're familiar with this idea. For example, we know that in humans we need to maintain a relatively stable body temperature in order to stay alive. If we start to get too hot with a fever, that can be dangerous. Or if our body temperature gets too low, we become hypothermic, we run into problems. Okay. We also need to maintain plasma pH and plasma sodium levels within relatively narrow limits in order to stay alive. This is a picture of my dog. I think we know that the dog has to maintain body temperature above the temperature of the snow that she loves to run in when she's running around outdoors. But also in the summer, when she goes for a strenuous run with our daughter here, she's able to maintain body temperature at the same range, even though that outdoor temperature is dramatically different than the winter. Dogs aren't very good at cooling themselves compared with humans, so she often tries to change her environment to help maintain body temperature. Now, if homeostasis refers to maintaining a relatively stable environment, there are a couple of terms that are often confused with homeostasis that we should address. Those terms are balance and equilibrium. Let's start with equilibrium. If our body temperature were at equilibrium with room temperature, the two would be equal and we'd be dead. I actually took a couple of measurements just to have a look at this. And on the left side, this is an air thermometer. It says the room temperature is about 74.8. On the right, I used an infrared thermometer to get the temperature of the bricks behind the air thermometer. It read 74.6, well within the margin of error of those measuring devices. But let's take a closer look in a different environment. Let's take a minute to talk about systems at equilibrium. There are two important concepts I'd like to touch on. The first is, if a system is at equilibrium, changing one part of the system will change the other parts of the system. The second is, achieving equilibrium does not require energy. In fact, as a system approaches equilibrium, it will release energy. So let's look at the first part. Changing any part of a system at equilibrium will change the whole system. I have 2 glasses of water. The water levels are equal. They're connected by this tube, which is also filled with water. So what I'm going to do is take some food coloring in here. We'll color that water. And what we see is, if I add water to one side of this system, water will flow from this side of the system to the other until the water levels are equal. Now let's look at a different system. I have a big measuring cup and a smaller one. I know you can't read the numbers, but this reads about 500 milliliters of water in the larger measuring cup. The smaller one is at about 200 milliliters. Now if I add water to one side, I'm going to try to keep it at about 700 milliliters, so adding 200 to the left side. This has gained about 200 milliliters of water. What we find is, in the right side, I've added about 100 milliliters of water, maybe just under that. So when a system is at equilibrium, if you change one part of the system, you don't necessarily change the other side by the same amount. We don't add the same amount of water to each side of the system. But we add water until forces on each side of the system are equal. In this case, the weight of water on the left side is equal to the weight of water on the right side. Okay, another important property about equilibrium. As a system achieves equilibrium, it doesn't take any energy. The change in water levels has been happening on its own. As soon as water is added on one side, it will automatically try to shift the water to the other side. But it's more than that. As systems move to equilibrium, they release energy, and that energy can be used to do work, like lift a ball. So if I add water on this side of the system. Try to not mess with anything. So I can lift the ball up on the other side. I wanted to lift it up enough to pop it out, but it's not floating high enough. The term homeostasis is not synonymous with balance. In a balanced system, changes in one side of the system can be offset by changing the other side of the system. That might require energy, but still both sides of the system change. In this particular system, the right side of the system doesn't look exactly the same as the left. I've got 8 chips on the right side of the system and only 4 on the left, but because I'm using a lever, I can keep this system in balance. If I add 2 chips to the right side of the system, then I could offset that change by adding 1 to the left side of the system to rebalance the system. The key is both sides of the system changed. If we're going to maintain homeostasis, we can't change the internal environment. So no matter what happens, if this is the external environment on the right side, if I add chips, then I'll offset that change in the external environment through the expenditure of energy. If I remove all the chips, I'll push in the opposite direction to maintain the state of this system without changing the number of chips in the internal environment. So in order to maintain homeostasis, we have to be able to resist changes in the external environment to maintain what's going on inside our bodies. As we go through anatomy and physiology, we're going to see a lot of cool examples of this. One of my favorite examples in terms of maintaining blood sodium levels is a salmon. Okay, so salmon are born in a river in fresh water. They need to maintain blood sodium levels. There's not a lot of sodium around in the river, so they have pumps that will actively pump sodium from the environment into the bloodstream to help maintain those elevated levels. On the other hand, they'll swim out to the ocean and live in an environment where the salt concentrations are a lot higher than the blood. In that case, the pumps will actually reverse the way they pump sodium and pump sodium from the blood back out into the environment so that the levels of sodium in the blood don't change. So maintenance of homeostasis requires a process by which any change in the internal environment is corrected by bringing about the opposite change. If we get too warm, we need to cool off. If we get too cold, we need to warm up. The name of this process is negative feedback, and that's going to be the topic of our next video.